I'm sure I'm going to get quite a bit of copyright strike in this episode, but let's go through it anyways. First off, I just want to share with you a video that we covered last day on length contraction.
At a fixed speed in a fixed direction. Now, even with that restriction to that special kind of motion, Einstein realized that you could extract some deep insights into the nature of reality. He was able to figure out that at constant velocity motion, an object would be squeezed, it would be compressed along the direction of that motion. And if you want a more realistic version of that, you can have a taxi cab moving down Fifth Avenue going at very high speeds. That taxi cab would appear to be compressed along the direction in which it's moving. And in fact, if you were to jump in to that taxi cab, Einstein's insights tell us that the outside world would undergo some really wild-looking distortions because of the impact of constant velocity motion on space and on time. Deep inside.
Once again, the way how George sees himself will be different than how Helen will perceive him. So when Helen's watching George right now, she has a little crush on him because he looks like a rather slim, handsome gentleman. All right, so let's just talk about these two different lengths. There's a length that George sees himself at as he's rest relative to himself, and this is known as the rest length, and we'll denote it with L0. And then there's the relativistic length, or his contracted length, and this is L. So anytime that you see a knot in it, it's telling you about an object that is stationary. Kind of like our time, proper time versus our dilated time. Once again, as a reminder, the compression only happens in the direction of motion. So since George is standing upright over here, he will be slender while upright. On the other hand, if he ended up holding himself like this while traveling, well then from Helen's perspective, he'll look like some squished up dude that looks like that. Okay? Alright, so this spaceship that's traveling ridiculously fast appears only to be this long, at least from our perspective. So the question is, what is the proper length, or what's the actual length of the ship, which is quite a bit longer. So you go through and you'd sub these values into the formula and slowly calculate it out. One thing as a reminder, we're trying to look for the rest length. So you need to take this entire radical and bring it underneath. So you need to divide it to get to your answer. Here's another online video describing this really interesting thing called the barn door paradox. How do you get a crazy long ladder into a relatively tiny little barn? Here we go.
Hi guys, I'm Jade, you're watching Up and Atom, and today we're diving into the weird and wonderful world of relativity with an Einsteinian paradox. Needless to say, get ready for your mind to be blown, and then blown again. And make sure you stick around to the end because the solution to this paradox is pretty juicy. So there's a mysterious pole vaulter. Let's call her Alberta. Alberta is running toward a bar which just happens to be on a farm. This farm is pretty small, so she needs to run through an open barn on her way. Earlier that day, she was curious about the length of her pole, so she measured it against the side of the barn and found it was exactly twice its length. Knowing nothing about a strange pole vaulter running around the farm, you're busy working on a new contraption in there. You've set up a timer where, when it goes off, signals to the front and back doors of the barn to simultaneously close and open again. You go out to see if your contraption works, and just as the timer goes off, Alberta runs through the barn. So the question is, can both doors be closed with Alberta inside the barn? Well, no. I mean, we just said that the pole was twice the length of the barn, so there's no way she could fit inside if she were running at any kind of normal human speed. But let's make things interesting. What if Alberta was running at nearly the speed of light? This is where things start to get a bit crazy. When objects are traveling at nearly the speed of light, they actually contract in length. This is known as length contraction. So you might be thinking, yeah, cool, I mean, that makes sense. If an object is moving by really fast, my eyes don't have time to keep up with it, so it looks shorter than what it is. But it doesn't just look shorter, it actually is shorter. If you fire a meter-long missile at close to the speed of light and take a snapshot of it in mid-flight, it will actually measure to be less than 1 meter. By how much depends on how fast it's going. So if Alberta is running toward the barn at near light speed, from your reference frame, she contracts in length in the direction of travel. In other words, to you, she looks all squished up. So it's perfectly plausible that both doors can be closed with her inside, even if it's just for a split second. While this is all very bizarre, it still isn't a paradox until we consider things from Alberta's perspective. And why would her perspective be different from yours, I hear you ask? Well, because all motion is relative. Imagine you're at the train station watching a train go by. From your reference frame, you are standing stationary on the platform and it's the train that's whizzing past. Now imagine you're on that train. Now you are standing stationary on the train and it's the platform that's whizzing past. So you might be thinking, well, really it's the train that's moving, even if it doesn't seem that way. But think about this. Imagine you're floating up in space watching the train drive across the Earth. It's a very high-speed train, traveling at 1,000 miles an hour east to west. The Earth spins on its axis 1,000 miles an hour in the exact opposite direction. So to you up in space, it looks like the train is stationary and the Earth is moving. All motion is relative. Now let's get back to the barn. So far you're an observer watching a squished up Alberta run through the barn. The timer goes off, closing both doors with Alberta inside. They open again and she continues on at near line speed. The real paradox begins when we take a look from Alberta's reference frame, because to her, she's stationary and it's the barn that's moving toward her at nearly the speed of light. So then if the barn is what's moving, it's also what's getting squished up in length contraction. So there's no way that at any point Alberta could fit in the barn with both doors closed. So from your reference frame, Alberta easily fits in the barn, but from hers, it's impossible. So what's actually happening? I mean, surely you're not both right. Well, actually, you are. This is the juicy part. The solution lies in what we mean by the doors closing at the same time. Special relativity tells us that there is no absolute time. There are only reference frames. We experience different things happening at different times depending on where we are and how fast we're moving. The reason that you haven't experienced this and why you might not believe me is because these effects are only obvious at near light speeds. The fastest you've probably ever traveled was on an airplane, which are about 1/1,000,000th of the speed of light. Relativistic effects are pretty hard to detect when you're moving around so slowly. So if we look back at what's happening with Alberta and her pole, from your reference frame, the timer goes off and the signal reaches doors A and B at the exact same time, and so both doors shut simultaneously with Alberta safely inside. Now from Alberta's reference frame, the barn and its doors are all moving. Door A is effectively running away from the signal, so it takes a longer time to reach it because it has more distance to cover in the chase. Door B, on the other hand, is moving to meet the signal, so it takes a shorter time to reach it because it has less distance to cover. So put together, as Alberta enters the squished up barn, door B closes and quickly opens again, letting her through. And then once the back of her pole is inside, door A closes and opens again. Told you it was juicy. Thanks so much for watching, guys. I hope you enjoyed this video. If you did, make sure to give it a like and share it with a friend if you think that they would enjoy it. If this is your
Imagine today as a ridiculously hot and sunny day. I have a snowball with me, and let's say I toss that snowball into the distance. Before the snowball even has a chance to reach the ground, it completely melts away because it's so hot outside. There's actually some elementary particles that exist up there in the heavens, and they only have a lifespan of about 2/1,000,000th of a second before they completely disintegrate. Yet, that detector up there is able to detect it. How can it do that? Well, let's figure that out in today's episode. And here we are. All right, so muons, they're radiation that comes out from, outside deep space. And when it comes to the Earth, it does end up binding with the Earth's atmosphere and causing it to decay. And under its very short lifespan, which it only lasts for about 2.2 microseconds, it'll completely disappear before it even has a chance, making it near the surface. But we're still able to detect it. All right. First off, let's just go through the classical math. All right. So according to Newtonian mechanics, if d is equal to v delta t, then technically speaking, when you go through all the math over here, it only has a chance of traveling, less than a kilometer through the Earth's atmosphere. Yet, when I was taking that video, which was on the top of Sulphur Mountain, if you ever have a chance to go out there, there was a weather tower at the top, and then scientists realized that, hey, let's geek this out. So, there are beds in there if you have a chance to check it out. They converted it to a cosmic radiation detector, and it's able to detect those muons before they completely disintegrate. And how exactly does that happen? Well, let's go through the math right now. All right, so we can either take this solution either from the perspective of time or from length. All right, for one thing, as the muons are traveling, they may only last and survive only for 2.2 microseconds, but time dilates from our frame of reference. So from where we're standing, it has a lot more time to travel. So when you sit down and you go through the calculations, you find out that it has about 7 times more time to travel before it decays. And if you multiply that by the speed that it's traveling at, then it has a chance to travel almost 5 kilometers before completely decomposing away. Another way of seeing this problem is by taking a look at it from length, right? So from our perspective, yeah, it has to travel very far, but the question is, what does it see it from as it's traveling rather quickly? As you may recall from the earlier video, space does really warp as you're traveling really quickly. So when you sit down and you go through all the calculations, it sees the length as much shorter. It sees that it only has to travel about 3/4 of a kilometer, and that's how it's able to successfully be detected at the top of that mountain. Here's another trippy example. All right, George and Helen. As George is skidding by Helen, suddenly a lightning storm strikes and hits both trees simultaneously. And the question is, what does Helen see and what does George see? All right, let's slow down just by a bit and let's just see it from Helen's perspective. All right, so lightning strikes both trees at once, and you can see the wave fronts approaching Helen and reaching her eyes at the same time as she is equidistant away from both trees. Well, let's take a look at it from George's perspective now, as if George was stationary and Helen was moving. And you'll notice that from this frame of reference, George will see the lightning strike happening on the right tree first before he even observes that strike from the left tree. What this is getting at is that, what we observe is really based from our frame of reference. And that's known as the simultaneity of events. All right, with regards to momentum, you might be used to the formula as this. Momentum is equal to mass times velocity. Yes, it is a vector quantity for momentum, all right? And this formula works really well if you're traveling very, very slow. How slow is very, very slow? Well, pretty much as fast as we can realistically get here on Earth, all right, with us traveling, even on a fighter jet. That's still very, very slow. So this formula works fine for us, all right? But if you decide to extract this formula all the way across, well, you'll notice for one thing, momentum and velocity, they are directly correlated, right? So as your velocity increases, your momentum should increase as well. However, there is a speed barrier that Einstein talked about, which emphasizes that nothing can travel faster than the speed of light. So what exactly happens here then? Well, the curve looks more like this. So in other words, when we're traveling at really slow speeds, yes, momentum is equal to mass times velocity. That's perfectly fine. But as we get closer and closer to our theoretical speed barrier, or actual speed barrier, then things break down and our momentum increases exponentially. So how do we factor that into the formula? Well, what we need to do is that we need to take our relativistic mass and our rest mass and sub it into our momentum equation. And there you have it. There's the magical formula to solve for momentum when you're traveling really fast. Do you need to use this formula all the time? Not really. As long as you're traveling slower than the speed of light, you can just use a simplified formula. And, as a good practice, as long as you're traveling, at least 1,000 times slower than the speed of light, you could probably ditch this and you'll be okay. Within 1% error. All right, but any closer, for example, if you're traveling at 1% of the speed of light or even 10% of the speed of light, you'll want to use the proper formula in those cases. So let's go through that. All right, let's take a look at the momentum of an electron using the proper calculation versus using the lazier calculation. All right, now if you use the lazy calculation, which is rho is equal to mv, you end up getting this number over here. However, this number is far, far off from the correct answer, which is about 7 times as great. All right, so your momentum increases quite significantly. This also brings up another important thing. There's a common misconception people think of in an electric circuit that electrons, when they travel through, for example, let's say you close this light switch, and then you'll see the light bulb turning on pretty much at the speed of light, right? So you think that the electric circuit's current will be flowing, at 3 times 10 to the 8 meters per second. Or sorry, let's draw this from the other perspective, because we know that protons can't move; it's electrons that move. All right, so the current of the electrons move in this direction over here, and we might be fooled into thinking that they travel at 3 times 10 to the 8 meters per second. Well, that means that if they get around a corner, they'll just shoot off and fly into the distance, which sounds rather ridiculous. All right. Moreover, if you take a look at the momentum has increased by about 7 times, so the amount of energy required towards moving the electrons increases significantly as well. All right, to the point where you're spending more energy moving the electron than lighting up the light bulb. So it doesn't make any sense at all. So realistically, what's happening in the circuit is that the electrons, yeah, they're moving, but there are bajillions and bajillions of them moving, and that's what causes this whole relativistic thing to happen, and it also causes magnetism to occur as well, and I'll show you some last videos with it. But before I finish off, I just want to mention these electrons, when they drift, it's called the drift velocity if you're curious. When they move through a circuit, they move pretty slow. They only move, around a centimeter per second or so, even if your current is rather high at a few amperes. All right, so yeah, it'll take a very long time for an electron to really move throughout an entire circuit. A very, very long time. Anyways, I'll finish off with these 2 more YouTube videos that you can find on the internet.
If you take a piece of wood and put it next to another piece of wood, nothing happens. And if you take a piece of granite and put it next to another rock, still nothing. But if you take this piece of iron and put it next to this other piece of iron, magnet. Magnetic objects are able to magically attract at long distances because they generate magnetic fields that extend invisibly out beyond the object. But the mystery is this: where do magnetic fields come from?
Well, that's easy, Henry. We've known for a long time that electricity and magnetism are really just two sides of the same coin. Kind of like mass and energy or time and space. They can be transformed into one another. And in fact, a magnetic field is just what an electric field becomes when an electrically charged object starts moving.
That makes sense for explaining why a current of electrons flowing through a wire causes this compass needle to move, or how currents in the Earth's outer core generate the geomagnetic field. But a bar magnet or the compass needle itself are just pieces of metal without any electrical current running through them.
Or are they? At the microscopic level, there are loads of electrons whizzing around the atoms and molecules that make up any solid.
Right. This brings up an excellent point. The magnetic behavior of any everyday object is influenced by a fascinating combination of effects ranging from the level of particles to atoms, collections of atoms, and collections of atoms. First, individual particles. Unlike the everyday workings of gravity and electricity, permanent magnets can only be fully understood as a quantum mechanical effect, in much the same way that particles like electrons and quarks have fundamental properties called mass and electrical charge. Most particles also have another intrinsic property called tiny magnet. Just kidding, it's called intrinsic magnetic moment, but really that's just technical mumbo-jumbo saying that particles with electric charge also happen to be tiny magnets.
If you want to know why they're tiny magnets, well, you may as well ask, why are particles charged in the first place? Or why do objects with mass and energy attract each other gravitationally? No one knows. We just know that's the way the universe works.
Exactly, and since the 1920s, we've known that each individual electron or proton is basically a tiny magnet, which brings us to the level of atoms. An atom is a bunch of positively charged protons with a bunch of negatively charged electrons whizzing around them. The proton tiny magnets are about 1,000 times weaker than the electron ones, so the nucleus of the atom has almost no effect on the magnetism of the atom as a whole.
And you might think that since many, though not all, of the electrons are also moving, that like the current in a wire, they should generate magnetic fields due to that motion. And indeed they do. These are called orbital magnetic fields.
Except these don't usually contribute to the magnetic field of an atom. Here's why. Electrons in atoms are accurately and complicatedly described by quantum mechanics, but the gist of the story is that electrons congregate in shells around the nucleus. The electrons in any filled shell zoom equally in all directions, so the currents they generate cancel out and generate no magnetic field. These electrons also come in pairs whose tiny magnets point in opposite directions and also cancel. However, in a half-filled shell, all of the electrons are unpaired, and their tiny magnets point in the same direction and add up, meaning that it's the intrinsic magnetism of the electrons in the outer shell that gives an atom the majority of its magnetic field. So atoms near the side of any of the major blocks of the periodic table, which have full or nearly full outer electron shells, aren't magnetic, and atoms in the middle of the blocks have half-full outer electron shells and are magnetic. For example, nickel, cobalt, iron, manganese, chromium, etc.
Wait, but chromium isn't magnetic.
But just because an atom is magnetic doesn't mean that a material made up of lots of that atom will be magnetic, which brings us to the level of crystals. When a bunch of magnetic atoms get together to make a solid, they generally have two options. One is for all the atoms to align their magnetic fields with each other, or they can align their magnetic fields in an alternating fashion so they all cancel out. The atoms will do whichever one requires less energy.
That's why chromium, for example, is a very magnetic atom but a very unmagnetic solid, because it's one of the most anti-ferromagnetic materials that we know. Iron, on the other hand, is the namesake of ferromagnetism, so it is unsurprisingly ferromagnetic, or, in usual parlance, magnetic.
Sometimes. The last and final level of magnetism is that of domains. Essentially, even in a magnetic material where the magnetic fields of atoms line up together, it's possible that one chunk of the material will have all its atoms lined up pointing one way, and another chunk will have all its atoms pointing another way, and so on.
If all of these domains are of a similar size, then none may be strong enough to force the others to align with it. In which case, a piece of iron, for example, may have no magnetic field at all because of all the warring magnetic kingdoms within it.
However, if you apply a strong enough magnetic field from outside the material, you can help one domain expand its control over its neighbors, and so on, until all of the domains have been unified into one kingdom, all pointing in the same direction.
And now, finally, you can rule with an iron fist. I mean, magnet. It's magnetic because it's ferromagnetic and all of the domains are aligned.
Exactly. What's remarkable is that magnetism is a fundamentally quantum property amplified to the size of everyday objects. Every permanent magnet is a reminder that quantum mechanics underlies our universe. In order for an everyday object to be magnetic, though, it has to have a unified kingdom of magnetic domains, each made up of bajillions of magnetic atoms which also need to be aligned with each other, each of which can only be magnetic in the first place if it has an approximately half-filled outer shell of electrons, so their intrinsic magnetic fields can align and not cancel each other out. Not surprisingly, these criteria are pretty difficult to fulfill, which is why there are only a limited number of suitable materials you can use when you're building a magnet.
Or you could just run a current through any electrical conductor and produce a magnetic field that way.
But hey, why does that work in the first place? Click here to go over to Veritasium and we'll find out what special relativity and the speed of light have to do with electromagnets.
Yeah, let's go check that out.
Only a few elements can be permanent magnets. Iron is one. Copper is not. But if you pass an electric current through any metal, it becomes a magnet. An electromagnet. But how does this work? Well, strangely enough, it's a consequence of special relativity.
Special relativity is the fact that in our universe, length and time aren't absolute. They're perceived differently by observers moving relative to each other, hence relativity. For example, if you measure carefully enough, you'll find that time passes slower for observers moving relative to you. Hey Derek, when did you last shave?
6 hours ago. Actually, it was 5 hours, 59 minutes, and 59.99999999999 seconds.
And moving objects are also contracted in their direction of motion.
You're looking slim, only in your frame of reference. So when an object is moving relative to you, it actually takes up less space than when it's not moving. And even though this effect is obviously way tinier than we've shown, length contraction is what makes an electromagnet work. Picture a copper wire. It consists of positive metal ions swimming in a sea of free negative electrons. Now the number of protons is equal to the number of negative electrons, so overall the wire is neutral. So if there were a positively charged cat nearby, it would experience no force from the wire at all. And even if there were a current in the wire, the electrons would just be drifting in one direction, but the density of positive and negative charges would still be the same, and so the wire would be neutral, so no force on the kitty. But what if the cat starts moving? Imagine, for simplicity, that the cat is moving in the same direction as the electrons with the same velocity. Well, now, in my frame of reference, the wire is still neutral, and so there should be no force on the cat. But consider the same situation in her frame of reference.
In the cat's frame of reference, the positive charges in the wire are moving, so according to special relativity, their separation will be ever so slightly contracted. Also, from this perspective, the electrons aren't moving, so they'll be more spread out than before. Remember, objects take up more space when they're not moving than when they are. These two changes together mean there's a higher density of positive charges in the wire, so it's no longer neutral, it's positively charged, which means that the positively charged cat will feel a repulsive electric force from the wire.
But in my frame of reference, this seems mysterious. There's no force on a stationary charged cat, but a moving cat is somehow repelled from this neutral wire. How do you account for that force? Well, we say it is the magnetic force. And that's mainly because a wire with current in it deflects nearby magnets. So really what this experiment shows is that a magnetic field is just an electric field viewed from a different frame of reference. In the cat's frame of reference, it is repelled from the wire due to the electric field created by the excess positive charges produced by the effects of length contraction. In my frame of reference, the cat is repelled from a neutral wire due to the magnetic field created by the current flowing in the wire. So whether you see it as an electric or a magnetic field just depends on your frame of reference, but in either case, the results are the same. So an electromagnet is an everyday example of special relativity in action. Now that might seem crazy, since electrons drift through wires at about 0.00000000001% the speed of light. So how can special relativity have anything to do with it? Well, the truth is there are enough electrons in a wire, and the electric interaction is so amazingly strong that even the minuscule effects of length contraction can produce significant charge imbalances that produce a noticeable force.
So special relativity explains electromagnets. But what about permanent magnets?
Yeah, I mean, there can't be electrical currents flowing around inside lumps of rock, can there? Click here to go to Minute Physics, where we'll explore magnetite, compasses, and all the wizardry of permanent magnets.
Mind blown yet? Well, if you aren't mind blown yet, then by all means watch Henry's video again. And if you're already mind blown, don't worry. The homework tonight is a lot less intense. Best of luck!